John Dalton was a notorious scientist in the 1800s who contributed a considerable amount to atomic theory. His theory is based around the idea that atoms of different elements can be determined by their different weights. In 1803, he put forward 6 basic ideas to a lecture hall in the Royal Institution. All matter is composed of atoms. Atoms cannot be made or destroyed. All atoms of the same element are identical. Different elements have different types of atoms. Chemical reactions occur when atoms are rearranged, and compounds are formed from atoms of the constituent elements. However, he made a vital mistake by making the assumption that the simplest compound of 2 elements must be binary, formed from atoms of each element in a 1-to-1 ratio. Another mistake that Dalton made was that his system of atomic weights was not very accurate. For example, he gave oxygen an atomic weight of 7 instead of 8. However, even though he made these errors, Dalton's theory was a logical explanation of atomic theory, and these theories were the foundations for new fields of experiments in atomic theory. Dalton did experiments, worked out atomic weights, and invented symbols for atoms and molecules. It took time for Dalton's ideas to be accepted by scientists, as a few of his ideas were incorrect, about gases for example, and the evidence needed to support his theories couldn't be collected for many years, as the experiments which needed to be carried out to provide this vital evidence couldn't be carried out as atoms are too small to see. J.J. Thomson discovered the electron in 1897. In 1897, the British scientist Thomson discovered the electron in a series of experiments which studied the nature of electric discharge in a high-vacuum cathode ray tube, an area being investigated by numerous scientists at the time. Thomson interpreted the deflection of the rays by electrically charged plates and magnets as evidence of bodies much smaller than atoms that he calculated as having a very large value for the charge-to-mass ratio. He later estimated the value of the charge itself. He showed that the atom contained smaller pieces which Dalton had early believed to be untrue, as he thought that atoms could not be broken down into anything simpler. In 1904, Thomson put forward a suggestion for a model of the atom as a sphere of positive matter in which electrons are positioned by electrostatic forces, and this is known as the plum pudding model. He attempted to estimate the number of electrons in an atom by measuring the scattering of light, beta and gamma rays, and this vital research went on to lay the foundations for the research carried out by Thomson's own student Rutherford. Thomson carried out one last important discovery. He carried out an experiment focused on determining the nature of positively charged particles. His experiments and discoveries led to the development of the mass spectrograph. Thomson's assistant, Francis Aston, developed Thomson's machine further and created an improved version, which was able to discover isotopes in a large number of non-radioactive elements. Thomson received various honours during his lifetime, which included the Nobel Prize for Physics in 1906 and a knighthood in 1908. Ernest Rutherford published his atomic theory, which described the atom as having a central positive nucleus surrounded by negative electrons in an orbital energy levels, or shells. He fired alpha particles at gold foil. Most of the particles pass straight through the foil, which showed that the atom is mostly empty space. A very small but significant number, approximately 1 in 8,000, were deflected back to him at 90 degrees, which led him to the theory that there is a dense centre in the middle of the atom, the nucleus, which is positively charged. Much of an atom's charge is concentrated in a relatively tiny area in the centre of the atom, known today as the nucleus. This concentrated central mass and charge is responsible for deflecting both alpha and beta particles. Niels Bohr added to and developed Rutherford's model of the atom. He used experimental evidence which supported the idea of electrons occupying particular orbits or shells around the nucleus of an atom. Henry Moseley was a British chemist who was a student of Rutherford himself. Moseley worked on and developed the application of X-ray spectra, which helped him to work on atomic structure. Moseley discovered many things, and his results led to a more accurate positioning of elements in the periodic table. He did this by redetermining atomic numbers more closely. In 1913, Moseley told of his results of the measurements of wavelengths of the X-ray spectral lines of various elements. These results showed elements emitted wavelengths fitted with ordering elements by their atomic number. With the discovery of isotopes of elements at the time, it showed that atomic weight wasn't the only factor of placing elements in the periodic table, as Mendeleev, Mayers, and other people had suggested, but it is the properties of the elements which change with atomic number. When the atoms were now placed in the periodic table based on their atomic number, the slight problem with Mendeleev's periodic table had been solved. Moseley's work was vital to the modern periodic table being based on elements' atomic numbers.